Yeah, yeah. Can you hear me?
Yeah, I can
Yeah.
hear you, yes.
Let me give me a minute. I'll check it.
Yeah.
Yeah. And yeah, are there any doubts from the previous session? Like, do you have any doubts?
Yeah, I do. In terms of how do you find the ICR? I don't get that. How you do that? Like
Which one?
first, is there like, can you show me like the steps on finding the ICR? Like you can just do this question and
Uh,
I can understand the same idea. Like you can just do question 4 and 5
uh,
and then I can just understand it from there.
like you did not understand how we found out instantaneous center?
Yeah, like how do you find the ICR?
Yeah. So, okay.
So do you find the velocity direction of the velocities first and then you find the
Yeah, yeah,
perpendicular?
yeah, yeah. First, we'll have to find the directions of the respective points and then draw a perpendicular to it. Wherever wherever they intersect, that will be the instantaneous center.
Okay, okay.
Okay, let me solve this so you'll understand the fourth and fifth one.
Yeah, I think they're the same thing.
And now in this, I think I did briefly discuss about it in the last class. Uh, so whenever we have a disk and a flat plane, the point of contact would be the instantaneous center. Okay? After this, okay, is it okay?
1 second, 1 second.
So whenever the disk rolling on a flat plane, the point of contact at this instant would become the instantaneous center of the disk.
Okay,
Correct.
okay,
This is because as if it, no, this can be seen as if it is rolling about this point. Okay,
okay,
and when it rolls, when it rolls, a new point comes in contact, then that becomes the instantaneous center for the new time. Okay, the next time.
okay,
So for this instantaneous center, whatever the point that is there, what is the point of intersection of the flat plane and the disk would be the instantaneous center, and in this case, this would be the instantaneous center. Okay? And the whole disk can be seen as if it's rolling about this point O. And now, if I join O and B, okay, if I join O and B and draw a perpendicular to this line, this would become the direction of velocity at this point. Okay? Are you getting it? So
okay.
this perpendicular one would become the direct, would become
So
the
in this case, because you know it's a disk and it's rotating
yeah
and it's connected to a wall,
yeah
so you just know that's the ICR, and then
yes
you get the velocity based on the ICR.
yes. Having since I know that this O would be the instantaneous center, and I joined both O and B and draw a perpendicular to it, so that would become the direction of velocity at this instantaneous location at this time. Okay.
Okay.
Yeah. Now, how is that we find velocity? So we'll have to find the velocity of B. For that, now tell me what would be the velocity of B in this case? The velocity of B would be OB times the angular velocity of the disk.
Yep.
Now, what is the angular velocity of this? We don't know, correct? We still don't know what is the angular velocity of the disk. For that,
Yep.
uh, you can see in the question the velocity of point A has been given, which is the center of the disk. Okay?
Yeah, I did this question. What I did was I did VB is equal to OB times omega. VA is equal to OA times omega. And then I did
Yeah,
VA over OA to find omega.
yeah, correct. So and VA, the velocity of point A would be OA times omega of this.
Yeah.
Correct. And from this, I can find the omega of this, or else I can just divide these two equations. If I just divide these two equations, equation 1 divided by 2, I would get VB by VA would be equal to OB by OA. And from this, I can write VB as VA times OB by OA. Got it? Understand this equation? Okay.
Oh, sorry. What did you do?
So I have divided both the equations.
Oh, okay, got it.
The omega disk actually gets cancelled, and the remaining thing I've rearranged the remaining things. Okay.
Okay.
Now we know OA, right? We know OA because OA is the radius of the disk, correct? OA is actually the radius, and that's been given. And VA is also given in the question. The radius of the disk is given, VA is given. But how is that we find OB? We'll have to find OB, right? So you can see to
I
find
mean,
OB,
you can just find omega by doing VA by OA, right?
yeah. But we don't want one omega, right? So omega of disk is not actually needed. Actually, that's why this divided the equation. Had they
Oh,
asked the
okay.
omega, I could have found out the omega using the second equation because I know OA and VA. I could have found out the omega for this.
Okay.
Because it's not asked, so I just divided the equations.
So the velocity of D is OD times omega?
The velocity of D?
D, yeah.
No.
VD.
No.
Oh, no, but it's not on the disk, so it's not
Yeah,
omega.
D is not a point on the disk, right?
Yeah.
No, we can't find. No, for that we'll have to find the instantaneous center of this BD link. Okay? That we'll find out later. Okay?
On the speed. Okay.
For now, we first have to find the velocity of velocity of point B. Okay, and that is given by VA times OB by OA. We know OA, VA, but OB has to be found out. Okay? So how is that we can find out OB? You can see this angle is given as 45 degrees,
Yeah.
and this would be 90.
Yeah.
And this whole thing would be 135.
Yeah. So you can
And
do cos
yeah,
rule.
actually you can do cosine rule or cos rule. So from this, what would be cos rule from this? Let me call this as some. This is cos 135, right? Cos 135. Cos 135 degrees should be. Uh, uh,
OB is 0.25.
so OB, what is OB?
0.25. I did it before, so.
Okay, yeah, OB is. Oh, you
I mean,
already. Yeah, okay.
I've already calculated OB because I
Okay.
thought right. I'm not really sure what I did, like, and I'm very confused in this topic, but yeah, we can just go over it now.
So since you have already solved for, and VA, what is VA given us? 1.2.
V is 1.25.
Yeah, 1.25 meters per second. And OB is given as, what is that you got? 0.
0.25.
0.25. And what is OA? OA
Uh,
it's 1.8.
OA is 180 into 10 to the power -3. That's in
Okay,
meters, I'm saying.
okay. 180 times 10 power minus 3. Or else we can just, yeah, okay, 180 times 10 power minus 3. So what is this velocity?
VB?
Yeah, VB. 1.25
VB.
0.25 by 180 into 10 power minus 3.
Oh, I don't think, yeah, I don't have that yet. I'm sorry, I don't have a calculator right now.
Okay. I'll calculate. So it's 1.25 into 0.25 into 1000 divided by 180. So I'm getting it as 1.74. Actually, I'm getting it as 1.736 meters per second, but let me approximate it to 1.74.
Yeah.
So this would be the velocity of B. And since we know the velocity of B, now I'm interested in finding this angle actually. Let me call it as some
Okay.
x. So and the velocity of D will be along this
Why do you want to find that angle?
Yeah, I'll tell you. The
Okay.
velocity of D will be along this wall, correct?
Yeah.
It slides along this wall. And if you in the last class, if you remember, I did give the rigid link concept, correct? Suppose
So what
if I have the concept of rigid link, like how the velocities are related and the, let me explain. I'll also explain once again. Suppose see this. Let AB be one rigid link, okay, which is in some general motion, okay, and let the velocity of point A be VA, and let the velocity of point B be some VB. And these are the respective directions. Let VA makes an angle of theta, which is along the line joining the points, and let the angle made by VB, let the angle made by VB along the line joining the points be alpha or phi. Okay, you understood it so far?
Oh, yeah.
Yeah. Now, what is the component of VA along the line? It is VA cos theta, right? And similarly, component of VB along this line would be VB cos phi, right?
Yeah.
And they must be equal, correct? They have.
Yeah.
This is because AB is a rigid. Okay? So they'll have to be equal, or else if it's not rigid, actually the rod would extend, but that's not the case, correct? It's given as rigidly, so this has to be.
Yeah.
So let me, and for that, what is that I need? So to use the concept of rigid link, I must have whatever the velocity, the directions they make with the line joining the points. I need these two angles, correct? If I have these two angles, I can use the correct?
Okay. So you're going to find
Yeah.
VB
So
cos
whatever this
theta and then equal that to VD.
yeah, that's it. Since I already
VD
know VB,
cos VD
yeah,
is in the cos direction, so it looks at.
yeah. VB, I know the velocity of VB, correct? We just found out, and I don't know what VD is, but I definitely know what this VD makes with this angle. Let it be some theta, okay, or let it be some phi. And now I can use the concept of rigid link. That means VB cos x must be equal to VD cos phi.
Yeah, but you need to find phi, right?
Yeah, yeah, we'll find it because the lengths have been given. So we can find x and phi. VB is known. From this, I can find VD.
Yeah.
So that's what our first question is: magnitude and direction of this. Okay? So let's find out these angles. Okay, are you getting it? So, and or else this can be solved in other way. We can also solve for VD using the instantaneous center method. Okay. So which one do you want me to solve? Which one?
You can either okay to the instantaneous center just because I want to learn that. And then you can tell me about the other method as well.
Let's solve with this method, and we'll also solve using both the methods.
Okay, fine. Yeah.
And yeah, now what is that I need? So this is the line joining the points, and this is what I need. One second. So this is what I need, x. Okay. And for that, if I can find this angle, correct? If I can find this angle, then I can find x, because this whole angle is 90.
Yeah.
Yeah, if 90 minus whatever this angle is, let me call it as some a, angle A. So 90 minus angle A would be x, correct?
Yeah.
And if I can find, let me tell you what is that actually. So let me explain this, and this would also be phi, correct?
Yeah.
So this is how I can, and I can find this. So for this, I'll make some small construction. Let me drop a perpendicular here, okay, from B. So if I do that, and I can actually calculate this length of this perpendicular. Let me call it as some this length. How is that I can find this length? So this length would actually be equal to this. This length would be this, right?
Yeah. Yes.
And what would that be? Can you tell me? That would be that length would be. So let me call it as some point S. The length of BS would be R plus half times r cos 35. Correct. So this would also be 45. This would also be 45. And the
Yeah.
component of this along this would be half times r cos theta. So bs is half time r cos theta. And now what is that I should do? Let me also find these two angles. So let me call this some b, and from this, what is tan b? Not tan b. Since I know OB, let's find sin b. Sin b would be bs by OB, right?
Yeah.
And also, this is alpha, this is phi. From this triangle, from triangle BSD, what would be sin phi? Sin phi would be again BS by BD, right?
Yeah. Okay.
BD is given. BD is actually the length of the rod, so that we know, which is given as 720 mm. And BS we can find out. Actually, BS we found it actually. This is BS, so we can actually find phi, and we can also find B. That's how we can find X and all. Okay, are you getting it, like the construction and all? Like what is that I have done?
Yeah, I am. So you did sine phi is BS over BD, obviously.
Yes.
Okay.
And you also found out how sin B is BS by OB.
Yeah, I know that.
Yeah.
Yeah.
Let me find that out. Sin B is BS by OB. And what is BS? BS is actually R plus half R cos 45. R plus half times R cos 45 degrees. And OB we have already found out. What is OB? What is OB that we have found out? It's 0.25, right?
Yeah.
0.25 meters, correct?
Yes.
Let me multiply it with 10 for this so that it becomes 9. And R is given as, what is the value of
No,
radius?
it's 0.25 meters. So it's
Yeah,
already.
it's in meters, but the numerator will be in mm, right?
Ah,
So
yeah.
that
Okay.
so R is 180. R is radius is 180. Yes. So radius is 180 plus 180 by 2 cos 45 is 1 by root 2, and this would be 250 mm. So this, so 180 plus 90 by root 2 by 250. So let me quickly find this out. So 90 divided by root 2 plus 180 divided by 250, and sine inverse of answer 77 degrees. It's coming out to be 77.04. This B is coming out to 77.04 degrees. And similarly, let me also find sin phi. Sin phi is BS by BD. Actually, BD is actually the length of the bar. So BS is 180 plus 90 by root 2. And BS, what is the length of the rod? Length of the rod is 720 mm. It's 720 mm. Let me find this out. 90 divided by root 2 plus 180 divided by 720. And sine inverse, the answer, that would be 19.77 degrees. This is 19.77 degrees. So phi, sorry, that's not 19.77. Phi is 19. So this, I found out both the angles actually. And let me
Yes.
get that. And since I found out B and phi, so what would this be? This would be 180 minus B minus phi. So that's angle A. angle A would be, so from this triangle OB,
Yeah.
that would be 180 minus B minus 5. And what would be X now? So let me find it. So from this, from all this, A, angle A would be 180 minus B minus 5. And X would be 90 minus this, 90 minus A, but 90 minus 180 minus B minus 5. And this would be B plus 5 minus 90. And B is, what is that? We got B we got it as 77.04 degrees. And 5 we got it as 19.77 degrees minus 90. So that would be X. So let me quickly find out X. 77.04 plus 19.77 minus 90. So I'm getting it as 6.81 degrees. X is 6.81 degrees. So I got X, I got 5. So can I now can use this equation, correct? VB cos X is equal to VD cos Y.
Yeah.
So let me use that. So from the rigid link, since VD is a rigid link, so VB cos X must be equal to VD cos phi. So VD cos phi. And from this equation, I can say VD would be VB times cos X by cos phi. And VB, what is the velocity? What is VB? 1.74 meters per second. 1.74 times cos X is 6.81 degrees by cos phi is 5. Phi is 19.77. 19.77. Cos of 6.81 divided by cos of 19.77 times 1.74. So I'm getting it as 1.835. 1.8359 meters per second. I can, or else we can approximate it as 1.84 meters per second. So you understood it? Like how is that we found out?
1 second. So you did 1.74. Yeah, I got it.
And you understood the like the idea behind it, like correct? The whatever that we found out, first of all we found out VB using the concept of instantaneous center of the disk, and then we also found out X and phi. Then using the concept of rigid link, whatever these velocities, components of velocities along the bar should be equal, correct? That's what we have used.
Yeah, got it.
That's one method. And let's also solve the same.
So what is the answer again?
1.84.
Okay, got it.
Is it matching like the solutions that you have?
Let me a sec. I'm actually seeing it busy.
Maybe a difference in the decimal could be possible because we have approximated that sometimes.
1 second, it's right here. This is question 4.
Yeah, it's question 4.
That's weird.
Is there any? Is it not matching?
Oh, yeah. 1 second. I don't think I can find the answers. I thought, oh, it's here. It's here. From what time? He just recently uploaded the answers to this, so
No,
took a while.
we don't have answers.
No, now you do now. Yeah, he just uploaded it.
Okay.
He got 1.7 4, 8.
1.748, that's the velocity of B, right? Like we got the
VB.
velocity. No, we want BD, not BB. So what is it they're asking for, BB or BD?
Oh, no,
BBD?
you're right. Yeah, no, you're right. You're right. You are 1.847. Yeah, VD.
Yeah, I told you, right? The difference in decimal could was because I have approximated it times. Okay? So
Yeah, yes.
and
He did
see,
the ICR method as well.
yeah, let's do this. Let's solve the same using the ICR method. So let's solve the same thing. For that, I'll have to draw that. So let's solve the same using instantaneous entry. Okay. We have a disk. And it's on a platform. And B is somewhere here. This is O. And it's been joined with the link here. This is T. And this is O. This is B. This is B. And what is that we have done? So we actually have drawn a perpendicular to this. And we'll have to extend this, correct? What is it? That we'll have to drop a perpendicular to the direction of velocity, correct?
Yeah.
So let's do that. Okay. First, need some change.
And this ICR is only for rigid bodies, right?
Sorry.
You can only use this for rigid bodies, or can you use it
No,
for
no,
like?
no. You can use it for anything. Okay?
Oh, okay, okay.
This is the most general method. It doesn't have any this approximations or
And the
assumptions.
first thing you do if you're trying to find the ICR is to find the velocity of two specific points and then draw the perpendicular.
Yeah.
Um,
So to find out,
and
so
the ICR is relative to those two
yeah,
specific points.
yeah.
Okay.
In order to this ICR method, we can use this ICR method only if the directions of points are known, directions of velocities are known. And so if the directions of velocity are not known, we can't draw up a perpendicular to them, correct?
Yeah, yeah.
So that's the main thing. That's the important thing. Directions of velocity should be known, or else we can't use this method. Let this be D and C. And now this is a perpendicular. Okay? This is the direction of D, and I can draw. I can. So what is that I'm doing? This is BB, and this is BD, and I'm dropping a perpendicular. I'm dropping a perpendicular to the direction of velocity. Okay. And I'll also draw. So let this be this. This is a direction. This is a line perpendicular to BB's velocity. Now I'll also have to draw a perpendicular to BD velocity. Okay, this is a perpendicular to BD velocity, and this is a perpendicular to BB velocity. Now they meet at this point. Okay, this becomes the instantaneous center. You got it? Understood?
Yeah.
Yeah. And now let this be instantaneous center. Let me call it as O dash. Let me call it as O dash. Now tell me, if what would be the velocity of D here? The velocity of D here would be OD times, sorry, O dash D times the angular velocity of this about this point, whatever the angular velocity that this thing has about this point, angular velocity
Yeah.
of BD link, correct?
Yeah.
And how is it now? We have to find 2 points. So we have to find two things. O dash T needs to be found out and omega BD, correct? But
Yeah.
let's also use the instantaneous for point B. What is the velocity of point B? That would be O dash B times the velocity of the BD link, the angular velocity of the BD link, right?
It's VB, right?
Sorry.
That's O dash
Yeah.
B times the
Yeah.
V. Okay, yeah, got it.
And now I know VB, correct. VB is already found out. And if I can find out O dash B, or else let us do one thing. Oh, 1 second. Let me look into the question. Okay, they're also asking for the angular velocity of BD link. Let's find out.
Yeah, they are.
So let's not divide the equations so that we can actually find out the angular velocities. From this, if I can find out O dash B, so I can find angular velocity of the link, correct? Right? So,
Yeah.
and how is that we can find O dash B? How is that we can find O dash B from this?
Usually find the angles.
OB, I know BD, and I know this angle. I also know this angle, correct? So this would be 90 plus X because this is X.
Yeah.
So I know this, and I also know this angle as well. This is 5. So this should be 90 minus 5. So I know in this triangle O dash BD, I know 2 angles and 1 length, which is BD, correct?
Yeah.
And you know the you know this rule, like sine rule along with cosine rule. There is also sine rule.
Yeah, I know.
So how is that? So suppose if we have a
Nine,
triangle,
sine 90 plus alpha over
the ratio
OB.
of side and its and an angle opposite to the side would be same.
Yeah.
That's what sine rule is. So if I use in triangle, from triangle O dash BD, I can find out OD O dash D by sine of 90 minus X must be equal to what is the other thing? The other side is O dash B by sine of 90 minus 5. That must be equal to, and what would this angle be? We can find out this angle, correct? That would be, let me call it as some K, and K would be what? K should be 180 minus 90 plus X minus 90 minus 5, correct? Actually, this should be 90 plus X. I'm not confusing you, right? You got it, right?
No,
Yeah.
not at all.
This should be what? This should be 5 minus X actually. So 90, this 90 and this 90 gets cancelled with this 180, and we have plus 5 and minus X. So plus 5 is 19.77 degrees, and X is, let me find what X, what is X? X is 6.8. X is 6.8. That will be K, and let me find out K. 19.77 minus 6.81. So 12.96. It's 12.96 degrees. And what would be the third angle? The third angle would be OBD, BD by sine K. Correct? So this is what sine rule from triangle O dash BD. You got it so far?
Yeah.
Yeah, and we can use these two. We can use these two terms to find out for to find out O dash B, and we can use first and last terms to find O dash T.
So K is equal to 5 minus X, you said?
Sorry, K is this. K is from triangle O dash B. K should be 180 minus the summation of other two angles.
Yeah, got it.
Yeah. Oh, yeah. The summation of the subtraction of other two angles. Okay.
Yeah.
So that's how I found out K. And if I use 1 second from this, let's use the first and third term so that I'll get. Let's use these two equations, these two terms. From this, O dash B would be BD by sine K times sine 90 minus 5 would be cos 5. So from this, so BD, what is BD? BD is 720, right? BD is link L. What is the length? 720. Yeah. It's 720. 725. Sine K is 12.96 degrees. sorry, times cos 5, cos 5 is 19.77. 19.77. So that would be O dash B. Let me cos 19.77 divided by sine 12.96 times 720. So I'm getting it as 3021.17. So the length of O dash B is 3021.17 mm. And similarly, I can also find O dash D. So O dash D would be BD by sine K times and sine of 90 minus 6. That would be, so BD is 720 and sine K is sine 12.96 and sine 90 plus 90 minus 90 plus x would be cos x, but cos x is, what is x? 6.81. So that's 90 plus x value, right? Yeah, that should be 90 plus x. 1 second. That's x only. Right? That's x and dt, that should be 90 plus. Yeah. So let me find this out. So that should be cosine of 6.81.
Wait, isn't it 90 plus x?
Yeah, 90 plus x. Yeah.
Oh,
So
okay,
90
you wanted to find k, right?
k I have already found out. Here, you can see.
Yeah, so can you go down there 1 second? Um,
So
wait,
this
so
I've
how did you
equated
get cos 6.81 there?
sine 90.
Oh,
See,
90,
sine
90. Oh, okay, I didn't
there
see
is
that,
90, right?
sorry.
So
Yeah,
the ratio changes actually. Just
yeah,
ignore
yeah,
it.
yeah, yeah.
Or else you can use sine 90 plus only. That's also possible.
Yeah.
So you got it, right? 6 sine cos 6.81 divided by sine 12.96 times 720. So I'm getting it as, I'm getting O dash D as 3187.75 mm. 3187.75 mm. So now let me use this equation. VB is O dash B times omega BD. So from this omega BD, or the angular velocity of BD link would be, angular velocity of BD link should be VB by O dash B. And what is VB? What is VB that we got? 1 point, what is VB? Where is VB? 1.74 meters per second. 1.74 meters per second. And O dash B, we just found it out. O dash B is 3027, or else let me convert that into meters. That would be 3.02117 meters. So now the angular velocity would be 1.74 divided by 3.02. So I'm getting this 0.57 radians per second. 0.57 or 575. So let me approximate it. 0.56558 radians per second. You understood? Got it, right?
Yeah, yeah.
And what is the, this is the magnitude, but what
Wait, what is
could be
your
that?
answer again?
0.58 radians per second. Is it not matching?
I'm just making sure it is. No.
It's not
Wait, no, he isn't. I didn't get it yet. He got 0.98.
radians per second. What are his
One
units?
sec. Here's VD, then VB. I don't think. Oh no, you got 0.65. Yeah, you got 0.65 for omega BD.
Omega BD is 0.65 radians per second. That's what you got.
Yeah,
Now tell. Now I have two questions. What is its VB? What is its value of VB? Velocity of B? Is it 1.6?
VB.
Yeah. Is it 1.74?
No, it's 0.65.
The velocity of VB, the VB.
Yeah,
Then we got a different velocity, right? One second. Our VB is different. What is happening?
yeah, it's not looking at it right now.
One second. We got a different VB actually. And what is now? Tell me what is his length of OB from the disk? From the disk, what is his OB length?
OB, right?
Yeah,
Yeah, he got 251 millimeters.
251 millimeters. Okay. If and
I
what
just
is
rounded mine up, rounded
okay?
mine down,
What
sorry.
is velocity of V? And yeah, in that case, uh what OA is? OA is the radius, right? Yeah, OA is the radius, and which is given as 180 mm. So let me find this out. And one from this, one second. Yeah, let me find this out. It should be 1.251. 251 divided by 180 times 1.25. So I'm getting it as 1.74 meters per second. So why is that he is getting a different VB?
We check.
Can you send me? Can you send me that?
Yeah, I can.
But see, we also calculated VD with the same VB, but that we got right? How is that possible? We got
I
VD as
don't
one.
know.
Even he got VD as 1.84 meters per second, right?
Yeah,
Which
he
you
might have
already
made a
have.
mistake
Then
at
in
most.
in that in that VD we used same VB, which is this 1.74 to find out VD. But both answers are correct. So how is this
Yeah,
correct?
I don't know.
Right.
Sometimes he's kind of weird sometimes.
Okay. Okay. VB, see, VB is correct. VB is 1.74.
Yeah, that's good. At least VB you're saying, right?
Yeah, VB. So, see,
VB,
he's using a different VB, but he's both VD of us are matching.
his VD is 1.84, which,
Which we got 1.84.
yeah, 1.847. That's what he got.
How is that he's getting a different same VD
I
using
don't
a
know.
different VB? Maybe he might be wrong because VB is 1.71. It's very clear, right? It's very clear from this. So
Yeah, I
VA is
sent
given
it.
as 1.25, right? Yeah, VA is given as 1.25 in the question. In the question itself, it's
VA, you're saying?
VA. Yeah, VA is given in the question itself. Can you see? This is
Yeah,
1.25.
it's given 1.25, yeah.
So we are using 1.25, and so we are using same VB, same OA. So how is that is getting a different one?
I don't know.
Yeah, maybe you might have made a mistake.
I feel like he's made a mistake for sure.
Yeah, and yeah. So make angular velocity of BD link has to be this 0.58 radians per second. Okay?
How much is it? 0.58.
Yeah, 0.58 radians per second.
Okay.
And now let us find VD using instantaneous method. So that should be O dash D times omega BD. Right.
Yeah.
So now this should be, and we also have O dash D. So and let me find this in,
And you also have omega BD, so just
yeah,
multiply the two, right?
yeah, that's it. So this would be 3.18775 meters. So 3.18775 into 0.575. See, it's matching. I'm getting it as 1.823
Yeah.
meters per second, and if we can approximate it, it becomes 1.84. Okay.
So that means you were right from the
Yeah.
beginning.
So from both the methods, we are getting the same answer.
Yeah.
So you understood both the rigid link method and the instantaneous method. Actually,
Yeah, I got it.
they just ask for velocities. See, if you know the velocity of one point, and if they ask for the velocity of the other point, rigid link method is actually very handy. So it has got lesser steps when compared to the instantaneous center method. Correct.
Yeah,
So
because
all that,
rigid link, you need to find those angles, but the ICR requires those angles and even more
yeah,
steps, right?
yes. So
Okay.
the only thing that rigid link method requires is the angle that the velocities make with the bar. Okay, that's it. So if that
Okay.
is known, then what if that those angles are known? We just equate the components along the bar. That's it.
Okay.
That's and you can use either of the method. But the thing is, the one advantage with ICR method is it also gives us the angular velocity, correct? Which rigid link methods doesn't give, correct? So
Yeah.
rigid method it gives only the velocity of the other point if one of the velocities is known, and whereas the instantaneous center method gives the velocities of both the along with the velocities, it also gives the angular velocity of the link. So that's the advantage with this. So shall we move to the next one?
Right. This
And
one
you
was
try.
really confusing. I tried the previous one. It made more sense, but this one I didn't really understand.
First of all, in this question, this is a in this question actually the thing is we can't use we actually can't use the instantaneous method and the rigid link method because they are asking for the accelerations, not the velocities.
Okay,
Can you,
so when do you use the ICRs? Like when do you use the
yeah,
ICR
the
methods?
ICR method you can use for velocities. If no, in all the previous questions they were asking for just velocities, angular, be it angular velocity or linear velocity, whatever it may, we can use instantaneous center method.
Okay.
But you can see in this they're asking for the acceleration of the points. Okay, angular acceleration and linear acceleration. See, AC is linear acceleration, correct, because the point C glides along the wall, correct.
Yeah.
This would be the acceleration of point, correct. As this this moves in this direction, so this goes down and this moves along the wall like this in this direction, right.
Yeah.
And now they are asking for acceleration of this point. The thing is, we this can also be are have they taught you the vectorial approach, how to do use vectors and all to solve for
Uh,
like do you have any idea, like do you remember in any of the classes they
uh,
develop?
he breaks it down uh
Yeah,
into like two separate components and then he answers it. And then he uses like you can see the method that he uses in this in the thing I sent you.
okay, you have some, okay, I'm not seeing it. One second. This one is okay. Now what is that he's doing is using the general motion method, and that we can actually find out.
Yeah.
And where is this fifth question? Yeah. That's what I'm missing. He's using the vectorial approach actually. Um, one second, I'm looking into it. So these are all the answers.
All right.
So are these answers solved, written by our
Yeah,
friends?
yeah, he solved it.
Okay. So this is what I've taught. He's using the vectorial approach.
Yeah.
So he first found out the acceleration of point B, and he is using that acceleration. Yeah. And then
Oh,
what
is
is
he using the rigid link method
no no no
to
no.
find VB and like he do
No,
that?
it's not. He's not using the rigid line. It is just using the normal circular motion concept of
No, I'm
acceleration.
saying is there a so there's a rigid link rule for
No no no
velocities at 2 points or on a rigid link. Is there one for acceleration as well?
no no no. We don't have.
Okay.
So we'll have to use this. And
So
if
how
we
would
found
you find VAC depending on VB? Sorry, how do you find AC depending on AB?
AC dip, yeah, that's what I'm asking. So you can see in this question, alpha, BC, and LBC. See, I have a different method actually. See, I solve such problems. Uh, shall I give my method? I'll also talk about this. Okay.
Okay, sure.
My method is actually it doesn't make use of any vectors at all, and this method is called as constraint method actually, the method of constraints. So I make this wall as a reference one, the reference thing, and I let the distance of point C from this wall be x, and I can find out x. Now, how is it I can find out x? And I'll also I'll draw one. I'll drop the perpendicular. Now I can write x as LBC cos 45. So let me call it as some theta, and let me call this as some phi.
Yeah, but theta is known that it's 45.
Theta is known, but we'll have to give the general expression first. Okay, that would be LBC cos theta plus LBA sin cos phi. But
Yeah, yeah,
how is it written? And now this is what this is a general expression for the distance of C. Let me write xc from the reference line, correct? And if I
yeah.
if I if I differentiate this with respect to time, let me do dxc by dt. What is that I get? I will get the velocity of point C,
Velocity. Yeah,
and that would be LBC times, but theta changes with time, right? As it moves, as the link moves, theta changes and phi also changes, correct?
yeah.
And now what would be that? So what would be the differentiation of cos theta? It would be cos theta, differentiation of cos theta is minus sin theta, right?
Yeah,
Minus sin theta, and differentiation of theta would be d theta by dt, right? And similarly,
yeah.
that would be LBA. Length doesn't change. That's why LBA and LBC would be constant. So differentiation of cos phi would be minus sin phi and d phi by dt. Correct? That would be the velocity of point C. And what are these actually? What are d theta by dt and d phi by dt? D theta by dt and d phi by dt are basically
Angular.
angular
Uh,
velocities of the.
yes.
This is the angular velocity of link BC, and this would be the angular velocity of link BA. So that's
Yeah.
how I found out the velocity. And if I differentiate it once again,
You get
if I
angular acceleration.
I'll get the acceleration of point C.
Okay.
dx square c by dt. So that will be dvc by
Isn't
dtx.
it by dt squared?
Sorry? Yeah, yeah, yeah.
Isn't
And I'll get the acceleration again. And the thing is, LBC remains constant. LBC actually remains constant, and this needs to be actually,
cos theta?
yeah. We'll have we have
Oh, you have to.
yeah.
Okay, okay, okay.
The thing is, d omega bc by dt, and differentiation of sin theta remains same, and differentiation of sin theta becomes cos theta. That becomes minus cos theta omega bc, and we'll have to differentiate it again. So this becomes a big method. Okay, so let me not solve it. Let me not use it. Actually, it's getting bigger. But you understood the basic idea, right? They simply ask for velocities. This can be used, but the double differentiation is becoming a huge thing. So let me not go
Yeah.
into it.
You want to use this method then?
Yeah, let's use whatever they have taught. But you understood the idea, right?
No, no, I got the idea. Yeah, for sure.
So let me use a vectorial method only. For that, first of all, for that, acceleration of point A needs to be found out. Okay? Let's find out. So how is that we can find acceleration of point B? You can see uh, if I draw a perpendicular to that link BA, this would be perpendicular to link BA. And now this would be the tangential acceleration of B. Correct. And a line along the normal would be ABN. That would be the uh, normal acceleration, centripetal acceleration of B. Correct? You got these 2 points?
So a normal acceleration is
The centripetal
a
towards the center. Centripetal acceleration will always be towards
yeah,
it.
yeah, yeah, understood the
And
acceleration.
we'll also have a tangential acceleration because you can see that actually we have angular velocity, so that we'll also have tangential acceleration. Okay?
Yeah.
And how is that you find the tangential acceleration? Tangential acceleration you can find. So tangential acceleration would be uh, r alpha. Correct? You know this, right?
Yeah, r times alpha.
R times alpha. Correct. That would be tangential acceleration. And r is known. R is what? R is actually the length of BA link, which is given as 14 inches. 14 inches. And let's convert this into meters actually. What is 1 inch
Yeah, I
in
don't know why. Sometimes it gives in sheet as well.
actually, yeah, you live in US, right?
Yeah, I mean, I
Yeah,
study here at least.
yeah. Basically, I don't know why they don't follow this SI units, right? They follow inches,
No, they
pound.
follow imperial, which is really stupid. Like, I don't understand how they do it.
Yeah. You studied till 12th in India?
No, I studied in India for a bit, and then I studied in Dubai, and then I came here.
Oh, okay. So 40, what is 1 inch in meters? What is 1 inch? What is
I
14
could not tell you. I've not lived here long enough to understand inches.
Yeah, I think
Um,
1 inch. Let me find
inches
one
to meters, right?
meters. It's point
14 would be
point
point
three five
three
double
five
six.
five six. Yeah.
Point yeah, 14 14 inches is point 3566 meters. So that would be
He doesn't actually use imperial because he doesn't like it, but he just gives it to us to
so
confuse us sometimes.
in the exam also you will be getting these units. What are the
No, like he'll give us any units, and we just need to know how to use it or convert it. That's just how it
Okay,
works.
1.6.
It's annoying.
So 1.6 times 0.35556. That would be 0.56896. 0.568. So let's approximate it to 0.57 meters per second. So that's the tangential acceleration. And what would be the normal acceleration? ABN. The normal acceleration would be this r omega square, rv square by r, okay, whatever.
Yeah, anything.
That would be again 0.35. Actually, at this instant, you will not have any normal acceleration, because at this instant, omega is 0. Omega of the link is, you can see the omega of the link.
Oh, okay.
So that would be 0 actually.
No, is it always zero or is it
No.
in that specific? Like I'm
Uh,
saying, like because it's an
Initially, it's 0.
instantaneous.
Yeah, initially it's 0. No, as the rod moves along, it gains omega. At some other point, you'll have the normal acceleration. Okay?
No. What I'm trying to say is, if they ask us to find it's at that instant, at that point, like say it's a random point,
If
and
some other random
like,
point, it will have both velocities, because it moves. Initially, it was at rest actually. That's what omega equal to 0 is. Okay?
okay.
And as it moves, and it was at rest, but it starts with an angular acceleration of 1.2, 1.6 radian per second. But then at some angle, it no, as the time moves, it will gain angular velocity at some other instant. No, maybe at some other instant like this, it might have both the both ABN and ABT. And
Okay.
ABN at this instant would be r times omega square, whatever the angular velocity it gains at that particular time. Okay?
Okay.
But
Alright.
initially it's because it's starting at first, there is no omega. So since we don't have omega, so ABN would be 0 at this particular instant. Okay? At this particular instant.
Yeah.
So I'll write that so that will not have confusion, because it's 0 initially. So this will be 0. Actually, yeah, this should be meters per second because it's acceleration. Okay. And since we don't have since we don't have actually ABN, so whatever the ABT that you have, it will also be AB, correct? At this particular instant, correct? We don't have ABN at this instant. So if we had ABN at this instant, then acceleration at this point would have been somewhere like this, AB. That would have been
Okay.
under root ABT square plus ABN square.
Okay. So then why
Correct?
is if there's
But
an
since we don't have,
angular
since we don't,
velocity, uh,
you took angular velocity.
hello?
Hello.
No,
Yeah,
I'm
yeah.
saying if since we don't have angular velocity, then how do we have angular acceleration if it's starting at it's instantaneously at
Yeah.
rest?
I'll tell you. That's the thing actually. Though the velocity is 0, acceleration may not be 0. That's the thing actually. Suppose, let me tell you one thing. Suppose take a stone or something, you throw it into the sky, and as it moves the topmost point, its velocity becomes 0, correct?
Yeah.
But still it is under the gravity. There is still G acting on it, even at the topmost point. If G doesn't act, how would it return? Are you getting it?
Uh,
Correct. If there is no acceleration, it won't return, right? It stays at that particular point only. But it's still returning. There is G still acting on it. There is acceleration due to gravity is still acting on it, even though it reaches the topmost point where velocity is 0.
yeah,
Correct?
but acceleration's
So
definition change in
yeah,
velocity. If there's no
that's the
change
thing
in
actually.
velocity,
Yeah.
then how?
The thing is, though velocity becomes 0, there still be acceleration. Acceleration may or may
That's
not be 0.
very counterintuitive if you think about it.
Yeah. So though velocity is 0, acceleration may or may not be 0. It can be 0, it cannot be 0. It's not, and it's suppose if I think about a block on the ground, okay, it's at rest, its acceleration is 0 and velocity is also 0, correct?
Yeah.
So, and think about a rock that we have thrown into the sky. Uh, at the topmost point, though velocity is 0, acceleration is not 0. It's still under the acceleration due to gravity, which is plus v. Okay, and the same thing happens here as well. You understood?
Yeah, I got it.
Yeah. And since we don't have ABN at this instant, whatever ABT that we have, that will be the acceleration of B only, correct?
Okay. So acceleration of B is ABT is equal to AB.
Yeah. And what would be the acceleration of C? This will be the acceleration of C, correct? It can only be along the ground.
Yeah.
And we have two more directions. And now let me talk about the vectorial approach that has been used in this problem. So this vectorial problem actually it says in order to use the vectorial approach, you'll have to use the relative concept of relative velocity. And now you don't see the acceleration of the link standing on the ground. You'll have to be on one of the points, either B or C. Okay. You'll have to approach the movement of the link standing on one of the points. Okay.
Okay.
Now think that I'm at point B. I'm on point B. Okay. So when I'm at point B, then I can see the link BC to be rotating about B. Correct.
Yeah.
Correct. I don't see any movement in this direction, but I don't see. I only see as if C is rotating about B. Correct.
Yeah.
And suppose if I stand on this ground, I see I can look BC along along with rotation. It will also move in this direction. Correct. It is in some general random motion. Correct. So it's something like this. At this B is something like this, and at some other point B would be here. B would come like this BC link would be here, and some other points BC link comes here. Correct.
Yeah.
Sorry. I'm so sorry. C always stays on the ground. It will be something like this. B would be something here, and at some other point this would be something here. And if I look at if a person on the ground is observing, along with see BC is as well as rotating, and also is moving like this. Correct. If a person on the ground observes that link BC, but if a person if a person on sitting on BC observes the link, the only thing that he observes is only rotation about B. Okay.
Yeah.
You got that's whatever you observe sitting on B, that would be the relative velocity. Correct. That would be the velocity of the link with respect to B. Okay. And now let me call it as, and for that we'll have, let the velocity of point C. What would be the velocity of point C as observed by B? That would be something like this. Velocity of C as observed by B, that would be the perpendicular to the link. Correct. It would be the correct. It would, so whenever I join these 2 points, now B is like center of rotation, and when I join C, that should be perpendicular, right? And it is not just it's not the velocity of C actually in general, but it's velocity of C with respect to B. Okay, that needs to be written. Correct? Okay. And there will be something called as acceleration of C with respect to B. Sorry. That would be in this direction. There will be acceleration of C with respect to B tangential.
Yeah.
And
so
towards
then
B,
AC is normal.
There will be acceleration of C with respect to B normal.
Which is what, AC or, oh no, it's normal. Okay, got it.
Yeah, that's the centripetal acceleration, and this is centrifugal acceleration. And what would be ACT?
Yeah,
what would AC be with respect to T? Okay. Oh, sorry. What would this be? That would be radius of OB are actually BC. BC multiplied by angular acceleration of BC link, angular acceleration of C with respect to B. Got it?
Yeah.
So this is actually BC. Sorry, this is actually BC. The radius actually R alpha, correct? That is what the tangential acceleration. This is R and this is alpha. Got it? And what would be ACBN? What would be this? This would be BC times angular velocity of BC link whole square r omega square.
Oh yeah, yeah.
And now if I join these two, actually I can, so 1 second, as it moves along I can see, yeah, now I can shift this ABT like this. One second, please. Yeah. Okay. First of all, let us find this so that you'll understand it. Then now tell me what is that? What are the things that we'll have to find out? BC is already there, so we'll have to find out the angular acceleration of CB link and also the angular velocity of CB link, BC link. Okay.
Yeah.
Then how is that we find these two? So one second, let me. So did we also get the acceleration as 1 point something? Sorry, he's also getting. Okay. He's using speed. Okay. He's using the speeds per thing. Okay. Sorry, I got it. I got confused. So this is
Yeah, be careful with the imperial units.
so that's why. See, I think why is that we are getting different? Yeah, it's using feet per feet, using everything using feet.
I can just convert the final answer and then we can check it out.
Sorry.
I can just convert the final answer and we can see if it's the same.
Oh, yeah. Omega BC system at rest at this instant. So rotation about C. And how is that we found out alpha BC? I'm not getting how is that we found out alpha BC. Okay, alpha BC is to be found out. Yeah. Alpha BC is to be found out. Oh, now I got it. Now. And he also says this thing actually. The thing that he says is there is no angular velocity of the link at this instant. There is no angular velocity because you see angular velocity of OB link is also zero, correct? Angular it's starting from rest, right?
Yeah.
So if it's starting from rest, then angular velocity of BC's link also should be zero, right? Are you getting it? You got it?
Wait, sorry, what?
See, in this angular velocity of acceleration of C with respect to B and normal, we have this angular velocity of BC square, right? Here at this point.
Yeah.
See, since BA, the link AB initially was at rest, correct? Omega equal to 0. Since it is also at rest, BC should also be at rest, right? Because BC can only move when AB moves.
Yeah.
That means initially the angular velocity of BC should also be 0, right? At this instant.
Yeah.
So if you got it, you want to, and BC,
Yeah.
BC will gain velocity after some time. Okay, initially it is also at 0, correct?
Yes.
Are you getting? So if BC is 0, we can't have any normal component, correct? Just like how for link AB, we cannot have BC component as well. Are you getting?
Yeah, I got it. Yeah.
Yeah. The B actually the acceleration of CB
No,
normal.
you can have a tangential component, not a normal
Yeah,
component.
normal component can't be zero because the angular velocity of BC link initially is zero, right?
Yeah, so I'm saying you can't have a normal component.
Yeah, normal component we can't have. That's what
Yeah,
ACB. We can have tangential component because this all though BC is zero, acceleration can't be zero, correct? Just like how the contradictory statement. Like, it's not contradictory, just like we have discussed, correct? Maybe
yeah,
angular velocity can be
counterintuitive.
zero, but acceleration can't be zero, correct?
Yeah, yeah.
So we can still have alpha CB, but omega CB can't. Omega CB can be zero, but still we can have alpha CB. Okay.
Yes.
And so if omega BC is zero, then acceleration of whatever the acceleration of C with respect to B we have, it will only be along this tangential component. Okay.
Yeah.
Correct. Just like how we had for B. And now let's draw the triangle. Okay. Let's draw the triangle. You'll understand. So we have BC, we have point B, and the acceleration of B is something like this, correct? This is the direction of acceleration of B, right?
Yeah.
And now we also have the acceleration of C something like this. Correct?
Yeah.
And now let me draw this. And one thing, you know how to draw vectors, right? These are absolute accelerations, correct? These are absolute accelerations. These are not with respect to any these are standard accelerations, correct? With respect to ground, okay?
Yep.
A and
Yep.
AC. Now, and so when we have standard accelerations, those need to be represented. They must have the this we call head and tail, right? For a vector, this is head and this is tail.
Yes. Yes. Oh, so
So for standard acceleration, yeah,
you're doing RAB, so you're joining the that point to the ending of you're joining the head and the tail, right?
yeah. No. Absolute
To form
accelerations,
a vector
yeah.
triangle.
Vector triangle. See, absolute accelerations must have their tail connected. Okay, all the absolute accelerations must have their tail connected.
Okay. Okay.
Correct. Okay. That means the acceleration of B will be something like this. This is acceleration of B, and this is the uh, like the reference point, the ground you can say, and the acceleration of A is like this. Correct. They must have their tail connected.
Yeah.
And now, whatever now the side joining the third one, okay, that would be acceleration of C with respect to B. Okay. And why is that? And why is that I'm joining the tail of this relative acceleration to the head of B? Because this is defined with respect to B, right?
Yeah.
And now this head, which is this rectangle, which is this arrow mark, that becomes the reference point for this relative acceleration. Okay. And this, whatever this we have, this is ground, because first for general accelerations or absolute accelerations, ground was the reference point, because that's why they got their tail connected. But for this relative acceleration, this head becomes the reference point, correct? That's why I'm joining this tail. Are you getting it?
Yeah.
Got it. So that's no confusion, right? How I formed this triangle.
No, I didn't.
And what is now? What is this one? The third one. This one would be what is this? What is this? What is this? What is this? And that would be only this component, correct? We did not have this normal component because angular velocity of BC link becomes zero initially, correct?
Yeah.
And that would be, so basically this would be BC times alpha BC. Okay, R alpha. Got it?
Yeah.
And now we are almost there. So we can form just if it, and AB we already found out, right? AB is already found out. So we already found out AB. AB is just equal to ABT because ABN is zero because initially the angular velocity was zero. Right? So this becomes 5.7 meters per second square. So this is actually AB, and AB is known, and we can actually find this angle.
Okay, so AB is what again? Oh, you
AB,
found it earlier, right? 0.57.
yeah, 5.57 meter per second square. AB should be
Yep.
equal to ABT because ABN is 0.
Yes, yes, got it.
And that's the same thing with this actually. ACB is equal to BC into alpha BC because the ACBN was becoming 0. Right? So,
Yeah.
and that's, so now we'll have to go back to the question. So now let me erase it. Actually, it was messed up. Shall I draw a new one? That would be better. Actually. And let me draw another. So so this whole thing is a there is a question actually. We don't have that here. No? Okay, I'll have to draw here only. Yeah, I got the question. So we have something like this. And this is A, this is B, and we got connected like this. And this is C, this is B, and we'll have the acceleration of B perpendicular to the link A. So this is A, this is AB, AB actually. And now, what does A this makes with respect to this? This is AB, and what would this be angle? What would this angle be? You can see in this triangle, this is 30 degrees. So this would be 60. Okay?
Yeah, and that would be 30 as well, right?
That would be 30. That would be 30. So that's one thing. And this is AC. This is AC. And since AC and AB are absolute, I'm joining this at AB only. This is, they must have their,
Yeah.
this would become AC. And now the acceleration of A with respect to B is defined. So this becomes ACB, correct? And you can see if this is 30, then this should become 60. So this is 30. So this whole thing becomes 60 because this is perpendicular, right? This is perpendicular, this whole thing.
Yeah.
This is normal to the wall. So normal to this wall. So this should be perpendicular.
Yeah.
And we define one angle is known. And how is that we can find the other angles?
Just cos root, sine root.
One second. So we need one more angle actually. We need one more angle to in this triangle so that we can find the other angles. And one second. And one thing, yeah. What would this angle be? What would this angle be? So this thing, this is given as 45 degrees, right?
Yeah.
Right. And this ACB has to be perpendicular to BC, right? That we have. See, this ACB has to be perpendicular to BC, right? That's a tangential
To
component.
BC. Yes, yes.
And if that is BC, one second.
And
Then,
ACB is what, 90?
sorry?
Like, is it 90?
No. So this is 90, correct? This should be 90 actually.
Yeah, that's what I was
If
saying.
that is 90, so this will become 90.
Yeah.
This would become 90. And can we somehow find this?
Yeah, it's 30. 60, 30, 90. So then.
Yeah, this would also become 45, right? Correct. So it's like this.
Oh, yeah. Sorry.
Correct?
It is 40. Yeah, you're right.
That would also become 45. If that becomes 45, what would this be? In this triangle, this is 60. 60 plus 45, that would become 105. 105 minus 180, this would be 75.
Wait, sorry, how did you get 45 again?
It's like this. Okay, we have a line. Okay, we have a line. That line makes an angle of 45 degrees with horizontal. Okay,
Oh, I didn't see that. Okay, okay,
and
yeah.
that we have a perpendicular to the line, and we also have a horizontal. So actually, this and this are parallel. So this should be equal, right? Whatever the angle that I have,
Yeah,
this
yeah,
should be
yeah,
equal.
yeah, yeah.
Or else you can get it like this. So this must be
No,
45. This is 90. Okay, and
no, no, no.
it's like
I know. I just didn't see that 45. Yeah, I got it.
yeah.
I got it.
So that must be 45. And now let's go dead to this triangle. So we have the triangles actually. This is AC and this is AB and this is A, A of C with respect to B. And you know, right? Why is that I'm connecting this A of C with respect to the head of B? Because it is being that's that is being defined with respect to B actually. Okay. Then this arrow becomes the reference point. Okay. And this becomes the ground, which is the ground becomes the reference point for AC and AB. Correct?
Yeah.
Got it, right? So now we found out all the angles. This is 60, and acceleration of B is found out as 0.57 meters per second square. 0.57 meters per second square. We already found that meters per second square. And this we got it as 75 degrees, and this we got it as 45 degrees. Now we can use the sine rule actually. AC by sine B must, sorry, sine 75. AC by sine 75 must be equal to ACB by sine 60 must be equal to AB by sine 45. Got it?
Yeah.
And from this, what is ACB? From this, let's find first. Let's see first and third equations. First and third terms. So from this AC, I would get it as AB times sine 45, sine 75 by 45. So let me find this out. Sine 75 divided by sine 45, sine 45 into what is AB? AB again 0.57, 0.57. So I'm getting it as AC. I'm getting it as 0.77 meters per second square. 0.77 meters per second square. But it was but it's given in feet per second square. So let me convert this into feet so that you get the better idea. What is 1 meter in feet? 1 meter, 2 feet. It's 3 feet. Give it in meters.
2.52.
2.52. Okay.
Yeah.
2.52 times 0.77. That
No, 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 no. 0.77 is
oh,
uh
sorry. 2.77. What is it again? What is the
oh
conversion?
no. It's meters per second squared to feet per second squared, right?
Yeah, what is 1 feet? What is 1 meter? What is 1 meter equal to how many feet?
Meters to feet. 3.2 feet.
3 point
3.3 feet. 3.3 feet.
into 3.3 into 0.57. Yeah, you can see that that's matching with the 1.88 that is. Oh, it's not.
No, it's you gotta. It's
What is AB?
7.
I don't think so. It's 3.3 actually. It's not 3.3, I suppose. Let me put the value here itself. Okay? Let me ask the Google only. What is 0.77? 0.77 meter per second square.
I think you're right. AC is 2.55.
AC is 2.55 feet per second, right? Feet per second square.
Yeah.
Yeah.
I mean, you
So
got 2.52, so it's similar.
yeah. So yeah, and we can also find ACBs from the same using the third and second and third terms, right? ACB will now be equal to AB times sine 60 by sine 45, and we know ACB is again R ACB is again BC times alpha BC, correct? That's what ACB is.
Yeah.
Yeah, and they're asking us to find alpha BC actually. So from this alpha BC would be AB times sine 60 by sine 45, sine 60 into 1 by BC, 1 by BC. So that would be the answer. So now AB, what is AB? AB, we got it, AB I got it as 0.57, 0.57.
Wait, why did you do 1 by BC?
This BC goes to the other side.
Okay.
Yeah. So BC, what is BC? What is the length of BC given? Is it given or we'll have to find out?
Wait, no, can you go down 1 second?
Yeah, it's given. It's given 128 inches.
No, I was wondering, why did you do AB over? I don't get that.
Which one? Sorry.
Uh,
The second, the last, this statement. So this equation.
yeah, like,
So
how did you do?
I equated these two terms.
Yeah, okay.
And this sine 60 goes to the other side. So this is what I get. Sine 60 goes to the other side.
Yeah, and then that
But,
you
but
equated, that equation you equated to
yeah,
DC.
that's
Okay.
yeah. But ACB is BC times alpha BC, correct?
Yeah.
So that's how we equated. Okay, and I got alpha BC from this. Okay.
Yeah, got it.
Yeah. Now AB is 0.57 into sine 60. Sine 60 divided by sine 45 into ABC 0.57 divided by BC. BC is 28 inches, but what is 28 inches? 28 inches to feet. Sorry, 28 inches to meters. It's
I mean, you can just use feet. It doesn't matter because it's just numbers in the end of the day. So, and you already have the distance of AB and BC. So,
yeah, 0.98. Yeah, that's okay. I understood. You're asking me to use AB in feet per second square, right?
yeah. Just use AB in terms of feet because we have that, right? We know what AB is.
What is AB in feet per second square? I don't have that value. 1 second.
Yeah, I can just find out for you.
It's 1.866.
Okay.
1.866 into, yeah, sine 60 divided by sine 45 into 1.866 divided by 28 inches. But we need inches to feet, right?
Yeah, right. Yeah.
That would be 2.4 feet. 2.4 feet, I guess. Correct?
Yeah.
No, 2.33, right? Yeah.
Yep.
2.33. 2.333. So I'm getting it as 0.97. Is that matching? Yeah, 0.7. Yeah, 0.97 radians per second square. Okay. Alpha BC. So these are the two sub questions they're asking. So let me summarize it. So you have any doubts? What is that we have found out is, so they're asking for the acceleration of C and angular acceleration of DPC. For that, what is that we have found out is, first of all, we found out the acceleration of B. Acceleration of B can be found. B can have two accelerations actually, a tangential acceleration and a centripetal acceleration. Tangential acceleration will be given by AB times alpha, and normal acceleration is given by AB times omega square, but omega is initially 0 because it is starting from rest, so it can't have normal acceleration. Whatever the acceleration that B has, everything will be in tangential form. Okay.
Okay.
And so whatever ABT that we found out will be AB. Okay. Now will be to, in order to draw the vector, we'll have to find the acceleration of C with respect to B. Okay. With respect to B. For that, I'll have to sit on B. Okay. I should not observe BC link on the from the ground. I should be observing BC sitting on B. Okay. When I sit on B, I'll have two components of and when I sit on B, I can see C to be rotating about B. Correct. I can only see C to be rotating.
C is sliding on the ground, right? So how is it rotating?
C is sliding on the ground, but that to a person on the ground. Okay. Are you getting it? So you can see to be sliding only when you observe BC link on the ground, observing from the ground. Okay, are you getting it? But whenever you sit on the BC link, you don't observe. No, you don't observe C to be sliding. The only thing you see is C to be rotating about you.
Okay.
So that's what is relative acceleration. Okay?
All right.
The relative component. And when you sit on B, you just see C to be rotating, the point C to be rotating about you. That's it. Okay. Are you getting? Like
yeah, I got it.
It's the same thing. Like suppose you are in some train. Okay. You are in some train. You observe your co-passenger to be at rest, right? Correct. You and your there are two persons in a train. The one person will observe the other person to be at rest, correct? But as a person, if I observe both of the person on the platform, I see both of them to be moving, correct?
Yeah.
Are you getting the concept already? So suppose you have some think that you have some luggage, luggage, and see that won't be moving with respect to you in the train, right? Will your luggage move in the train as you observe?
No, this is relative motions, right? Yeah, no, I get it.
Yeah, I get it. That's what I was saying. And since that's what I'm saying. When you sit on B, you only observe C to be rotating about you, but not sliding. Okay, because you are also sliding. Correct. When both of you slide, you don't see actually the sliding component. You only see the rotating component. Are you getting? Even B is sliding.
No, I get what you're trying to say. It's just like it's hard to imagine if I'm standing on B for C to be rotating. I could just see it sliding on the ground.
It's yeah. That's what. So I can use multiple examples. Suppose I am in one car and you are also in one car. So suppose you are driving this car, I am driving this car, and only thing that, so if both are moving at the same velocity, I observe you to be at rest, right?
Yeah.
But we're actually moving. Right? So that's the thing. So when I sit on the link itself, of course it's hard to imagine, but as you sit on the link, you observe only C to be rotating about B because you are also sliding, correct? When C is also sliding and you are also sliding, correct? Even A also moves like this, correct? Sorry, even B also moves like this.
Like when you mean rotating, you mean it's lifting off ground. Like I'm imagining it like moving above ground and rotating like a hour hand on a clock. Is that what you're trying to say?
You can yeah, that's what you are getting confused, right? It won't lift off the ground, correct?
Yeah, it won't lift off the ground even if you
correct.
try to.
But it's like this, correct? But you are moving in downward direction, correct?
Yeah.
B moves like this, correct? 1 second. B moves like this, correct? As it rotates.
Yeah.
And 1 second. And whenever you are at this initial position, you C was here, correct, as observed by B, and now it's like this. It's like this. Now C will be moved to a new position and B will move to a new position. You observe, though it's on the ground itself, but you observe as it's making an angle. Okay, there's an angle made. Are you getting? This was with respect to and
no,
this
I
was
get
with
what you're
respect.
saying.
No, this is what you observe it to be rotating. Okay,
Yeah.
so that's it.
Okay, I got it. Yeah.
And now when you sit on, yeah, now you got it. Though it's sliding, it still makes an angle, correct? Because both are sliding, correct?
Yeah.
So see, that's what you are getting at. You are just observing C to on B, assuming B also to be at rest. If B is also to be, if you assume B also to be at rest, it's the only thing that C has to be is not it should lift off the ground, correct? But in this case, B is also sliding, correct?
Yeah.
So that's why, though it does, it looks as if it's getting lift off the ground, but it's not. It's not. Okay, the angle changes. Okay, with a new position of C and B. Okay? And when you sit on B and observe C, and again you will have two components: acceleration of C with respect to B tangential, acceleration of C with respect to B normal. You got it? Those 2 points.
Yeah.
And acceleration of C with respect to B tangential is given by BC times angular velocity of the CB length alpha CB, and acceleration of C with respect to B normal is given by BC times angular velocity of BC whole square. But initially the whole system was at rest, so BC will also be at rest. Correct. BC can only move when AB moves. That's why BC angular velocity of BC will also be 0. That's why you don't have angular velocity of C with respect to B normal component. Correct? You got it so far?
Yeah.
Then whatever the angular velocity of C with respect to B is nothing but angular velocity of C with respect to B tangential, which is BC times alpha BC. Okay. And with that, and that would be perpendicular to the BC component, because you are observing that to be sitting on like you are sitting on B. Okay. And if you can draw all those in a rectangle and use the cosine rule and all the angles, so that's how we get it. Get all the answers. You are getting it, the vectorial approach. This is what the vectorial approach I was talking about. Okay. Hello.
Yeah, no, I got the vectorial approach. So is
Yeah.
this the only way to solve such a question with the
See,
triangle?
yeah. The as far as accelerations are concerned, this is the only method.
Okay, all right.
But
And
as far as velocity is concerned, you can use the instantaneous center method and that. Okay.
okay, all right. So, oh, and also, oh yeah, so I have a test tomorrow on these topics.
Yeah.
So I just had a couple of questions. So in the first question, for example,
Okay. Which one?
like in this question, the first bit, uh, like if you scroll all the way up in the first question.
Oh, the collision one.
Yeah, the collision one.
Yeah.
Yeah, can you just go up there? So in that case, in there, um,
Yes.
yeah, there, so I can only use that formula, the linear momentum formula,
Yeah.
uh,
You
in
will
the
be.
n direction, yeah, not the t direction.
You can't use it. You can also use in T direction, but in T direction, there is no use if you use it in T direction, correct? Because the ball moves only in N direction after impact, correct? The ball B only moves in normal direction after the impact, correct? N direction. So
Okay,
it can't have any component along T. So even though if you use it, it will be of no use.
okay, because if you do like, and if it's in the component of t, you just have to replace all the accelerations in the linear momentum formula with the a of t uh,
Along,
acceleration.
yeah, you
I'm
will have
saying
to.
if.
Yes. So why is that you are getting acceleration? You will not talk anything about acceleration.
No, I'm not talking about acceleration, I'm talking about velocity, not
Yeah.
acceleration.
Yeah. So when you and the linear momentum conservation linear momentum is actually vector quantity. So whenever you use it, you use it in a particular direction. Okay. And when you use
Okay,
it in a
okay.
particular direction, you'll have to resolve every component along the direction.
Okay, okay. All
That's the
right.
thing.
And yeah. VAT, the yeah, I mean pretty much the rest is just the oh yeah, and also when can I can you know those equations where you do omega is equal to omega naught plus uh angular uh what's it
Which one?
called? The angular acceleration times t formulas. Like you relate the angular accelerations and the omegas to the
The second one?
kinematics equations, yeah, where
Yeah,
the
yeah.
acceleration is constant. So that's only when the acceleration is constant or the
Yeah,
acceleration is zero.
that's when only the angular acceleration alpha is constant. You can
So
use,
only you can only use those formulas when either one of those
yeah,
conditions
yeah.
are met.
No, whenever the angular acceleration of the rotating body is constant, only when that that condition is necessary. Okay.
And this is only angular acceleration.
Yeah, the angular acceleration alpha, which is represented with alpha. Okay, the rate of change of angular velocity is angular acceleration.
So if acceleration is zero, for example, just
If acceleration
acceleration.
if acceleration is zero, the body simply don't rotate. Correct? It rotates, but with a constant angular velocity. You don't see at any time. At every time, the angular velocity is constant only. What is that? You are they'll ask us to find.
Yeah, okay, okay, okay.
Correct?
That's true. Yeah.
And these equations are valid only when our angular acceleration is constant. Okay. If it is not constant, we can't use this the equations of motion.
Okay, okay, okay.
If alpha is rotated, suppose in this question it's alpha is given as some constant, but if it is changing with respect to time, then you can't use.
Okay, okay, okay. And in terms of the ICR method, the move is to always find the direction of the velocities and then
Yeah.
draw a perpendicular line.
The first thing you'll be doing in ICR is, so you'll be having 2 points, right? One and first point A and B. Then you
Yeah.
should the first thing that you have to do is you'll have to decide the direction of those 2 points. Okay, the direction of velocities of those 2 points. Okay, after you decide the
Okay.
direction of velocities, you will drop a perpendicular to their directions. Okay,
Okay, okay.
and
All
whenever
right.
they will be meeting at some point, that becomes the instantaneous center of that particular link. Okay.
Okay. And in question three, for example,
Yeah.
at point C, the velocity is through the rod, right? The
Yeah. Yeah.
direction of the velocity of
Yeah.
C.
That I've explained. Correct. Why is it through the rod? Because if it
Yeah,
is
yeah,
some
yeah.
angle, the rod will simply lift off the support. Correct.
Yeah, yeah.
So
So why can't it be towards the ground? Because that way it won't lift off. It would just be towards the ground.
and again, that's also one thing. It will be pushing the wall. Correct. That's a rigid link. Correct.
Yeah.
And again, it can't push the wall. It can't push the wall. It can't lift off the wall.
Why
The
can't it push the wall?
uh, because it's given rigid.
So if
There
it
will there won't be any deformations. Okay.
oh,
See,
okay,
if
that's
it
what you
can't
mean. Okay,
if it
got it,
can't
got it.
push if it can't compress if it can't get compressed, so it can't move. When it can't move, it can't have a component into that, right?
No, yeah, yeah, you're right, you're right.
The
Yeah.
only thing that it can have is just along the wire.
Okay, okay, okay.
And
And
yeah,
okay. No,
the
sorry, go ahead.
A can only slide along the wall. So you'll drop since you know the velocity directions of velocity to those 2 points, and you'll be dropping the perpendiculars to them, and wherever they meet, that would become the instantaneous center. And after you find out the instantaneous center, let me call it as O. Then you will join O and B. Okay.
Okay, no, no, I got it. Yeah,
Yeah.
yeah,
And since OB is known, the direction of the direction of BB has to be perpendicular to OB, right?
yeah, yeah.
That's how you decide the direction of BB. And you can't decide the direction of BB unless or until you find out the instantaneous center. Okay.
Okay, okay, understood.
Correct.
Yep.
You got it right. Yeah.
Yeah, and what else? That's
And see, if it's possible, better use the rigid link method. Okay. If we can.
okay, and the ICR when I'm looking at a question and saying find the velocity and the acceleration, for example, imagine not they're not given a question like that here, but I'm saying if they do find find the velocity and acceleration. So would I still use the ICR method?
Yeah, you can still use the ICR method to find the velocities, but to find out the
And
acceleration, you
then,
have to use a vectorial method. Just like what you have discussed the last.
okay, yeah, got it.
And be
Yeah,
careful.
that's about,
And be careful with the angular velocity. If it is given as initial angular velocity is 0, the normal components become 0. Okay.
okay,
So, or else you get stuck with there. Okay, how is that I can find this and all? Okay? And it has
yeah.
to be, and it has to be actually. If the normal component doesn't become 0, then it becomes a huge headache actually to solve using vectorial approach.
Okay.
I think
Also,
they will be giving the initial condition where angular velocity is 0 initially. So that's why they ask. That's when they ask you to find other things. Okay.
okay, and also, are there any other, like, like how you said a disk has wherever the point of contact the disk has is the ICR automatically. Are there
Yeah.
any other like objects or scenarios where like there's automatic points of ICR?
One thing is for this, and suppose if I have blocked if I have blocked kind of thing, like suppose once suppose let me use a slider plan mechanism. Suppose if I have blocked see I think that's the thing actually. No other. Yeah.
Only the disk?
Yeah, only the disk actually. Yeah. So only the for disk, right, the point of contact would become instantaneous.
Okay, all right. And is there like a quick way to just find the velocity direction, like just by looking at it? Like sometimes I just get confused. I think that's the biggest issue with me. Like I can't judge which way the velocity, like sometimes I
Uh,
get confused which direction the velocity is going towards.
See, think in
In terms
suppose
of like links and stuff like that, like if there's like
yeah,
rods and they're linked
uh,
together, like where would it go? Would it go
you can
upwards or downwards?
in this disk and link thing, which is fourth question, you can see this is there is a we have a disk, correct?
Yeah.
So sorry, so I have a disk.
Yeah, like if it wasn't a disk, how would you find like if the ICR if you didn't have an ICR, then what's the best approximate guess you would give the direction of EV?
No, that can't be found out actually. So you're asking in the disk, in case of disk, yeah? What is the problem?
Yeah, because if there's a disk, you can find the direction of EV,
Yeah.
right?
In the previous, in the third one, I can't find VB, I can't find BB unless or until I find the instantaneous center of the B that link. Okay. There is no
Okay,
way I can find the even in even I can't give an approximation. Oh, this would be like this and that. No? I can't find unless I find in the instantaneous center. See,
okay,
to
and
find
then
the direction of velocity,
uh-huh.
the one thing that needs to be known, instantaneous center has to be known. Okay, or else, the other easy things like it slides along the wall. Correct? If it slides along the wall, then we can easily decide, oh, this will be the direction of velocity. Correct.
Okay, all
So
right.
for any other
And
random
yeah,
point, instantaneous center has to be known. We can't simply judge. We can't give approximately anything.
okay, all right. Also, in this case, there's the instantaneous ICR on the disk, which
Yeah.
obviously cannot be applied outside the disk, yeah?
Sorry. The ICR.
Like the ICR, that's we instantly know because the disk is connected to the
Oh, yeah.
ground,
Yeah.
right? That
Yes.
ICR can only be applied within the disk.
Yeah, the only that's the instantaneous center for the disk. For any other point on the disk, not any other point apart from the which is not on the disk.
So VD obviously cannot be
No.
uh
D is
yeah,
not a point on the link on the disk, right?
yeah, you're right.
Only A and B were on the disk. Okay.
Yeah. Okay.
So and that instantaneous center will be for only that A, B, and for any point on the disk. That's it. For any point on the disk. So D will
Okay.
have a separate instantaneous center that we'll find out later. Okay, like
Okay.
we'll be dropping a perpendicular to B and a perpendicular to direction of velocity, and it would get connected somewhere. Okay,
All
that
right.
would become the instantaneous center of D.
Yeah, got it.
Yeah. Anything else?
No, nothing else. I
And
think we're done.
you have exam tomorrow?
Yeah, I have the exam tomorrow for these. I think I'll just revise the topics and the notes, and I'll do a couple more questions. Is
Yeah.
it okay if I just send you like questions if in
Yeah.
case
You
I
can
have
send
any
me.
doubts?
You can send me. I'll try to answer. Okay. I'll try to answer.
Okay, yeah, just over WhatsApp, just tell me if I'm doing it correctly or whatever. Yeah, something like
Yeah.
that.
You can send it to him. You'll send it to him.
Okay, all right.
You
Yep,
can send it. Okay. I'll be
yeah,
answering.
yeah.
For now, no doubts, right?
No, no doubts, no
Uh,
doubts.
shall we stop?
Yeah.
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 Thank you. You can send me.
Thank you very much.
Yeah.
Yeah, for sure. Thank you very much. Have a good day.
Yeah. Have a good day. And all the best for your exam.
Yeah, thank you so much.